Hello class. Today we're going to continue discussing integrals. Integrals are a mathematical way of summing up a function. They are also equal to the antiderivative of a function. They have an incredible amount of uses. In the last lecture, we discussed the growth of harmful algal blooms and determined that if you know how the net growth rate of an organism changes over time and calculate its integral, you can figure out how the population is changing in time. We also saw that if you know the rate of new positive coronavirus tests as a function of time and calculate its integral, you can figure out how many people have tested positive for the coronavirus. In this lecture, we will continue discussing the properties of integrals. We'll start by reviewing the definition of an integral, then we'll talk about what the difference is between a definite and an indefinite integral before we work on solving integrals and antiderivatives. All right, let's discuss some different ways that we could understand an integral. One way to think about an integral is by thinking about moving objects. If we have a function, f of t, that describes the velocity of an object as a function of time, then the integral of f of t with respect to t will be the distance that the object travels. For instance, if f of t is the vertical velocity of a rock that we launched with a catapult, then the integral of f of t will give us its height relative to the height it started at. As we discussed in the last toolbox, we could also use the integral to understand how the population of a species changes in time, if we know the net growth rate of the organism. If f of t is the net growth rate of an organism, then the integral of f of t dt is the abundance of the species. For instance, if we had measurements of the instantaneous net growth rates of Karenia brevis, the algae that causes harmful algal blooms along our coast, then we could integrate those growth rate measurements to determine the abundance of Karenia at any point in time. We can also define the integral as the antiderivative. If we have a function f of t and define another function g of t such that g of t equals some constant plus the integral of f of t, then the derivative of g of t with respect to t will be equal to f of t. So integration takes us from f of t to g of t, and differentiation takes us from g of t to f of t. The integral undoes the derivative, and the derivative undoes the integral. Another definition of an integral is that it is the area under a curve, or in other words, the net area between the function and 0. So for instance, take this function f of x, which is graphed in black on this slide. Note that the area between the function and the x-axis is colored in blue if f of x is positive, and it is colored in yellow if the function is negative. This means that the integral will be the area of the blue areas, will be the difference between the blue areas minus the area of the yellow areas. We can also think of the integral as being the sum of a function made over infinitesimally small intervals. You can think of a bunch of bar graphs reaching up to the top of our function. As we make those bars narrower and narrower, or in other words, make delta x smaller and smaller, we get more and more accurate estimates of the area under that function. We also have the limit definition of an integral. This is the very math-speaky definition of the integral. It tells us that the integral from x equals a to x equals b of f of x dx is equal to the limit as n approaches infinity of the sum from I equals 1 to n of delta x times f of x sub I, where delta x equals b minus a divided by n, and x sub I equals a plus delta x times I. Let's really quickly go through an example so that you can see what this actually means. On the graph on the right, I have a function f of x, shown in red, and we're going to integrate this function from x equals 2 to x equals 10, or in other words, we're going to find the area under the red curve and between the thick black lines. If we start off at n equals 2, we have two boxes that we are summing over, and it is obviously going to be a huge overestimate. However, as n gets bigger, delta x gets smaller, and the area in the blue boxes gets closer and closer to matching the area under the red curve. This is what the limit definition of the integral is really doing. It's calculating the area of n boxes that approximate our curve where n is the number of boxes. As we make more and more boxes, we get a more and more accurate estimate of the integral. As the number of boxes approaches 0, we will approach an exact solution to our integral. This is very much analogous to when we used the limit definition of the derivative to calculate the slope between 2 points as we made those points closer and closer together. Alright, now that we've covered these different definitions or ways of understanding integrals, let's talk about another important concept, the difference between a definite and an indefinite integral. Let's start with definite integrals. The technical definition of a definite integral states that if we have a function f of x that is continuous over the interval from a to b, and then we divide that interval from a to b up into n different subintervals of equal width delta x, and then we choose a value x sub I somewhere within each of those subintervals, then the definite integral of f of x from a to b is equal to the limit as n approaches infinity of the sum from I equals 1 to n of f of x sub I delta x. Okay, so that's the limit definition of an integral again. The definition of a definite integral really boils down to an integral that we can compute between two different points that we usually call a and b. You can also think of the definite integral as the signed area under a curve from the value a to the value b. So for instance, in this graph on the right, the definite integral of f of x from x equals a to x equals b is equal to the area of the two blue sections minus the area of the yellow section. One really important thing to keep in mind is that the definite integral of a function of only one variable should be a single scalar value. So as long as you choose actual numbers to plug in for a and b, that definite integral of f of x from a to b should just give you a number. It should not give you some other function back. Okay, that was a decent amount of information to take in. So let's actually work through an example to get a feel for the definite integral. I downloaded data showing the worldwide number of new positive tests for the COVID-19 disease as a function of time. It is, of course, kind of spiky data because the data was only reported as daily case results, and also the criteria for a positive test case occasionally changed, and the testing regimes within different countries have definitely changed over time. Since I don't want to work with spiky data like this, that in many cases represents spikes that correspond to changes in testing, rather than real changes in infection rate, I decided to fit a function to the data. This is very similar to the way that we fit functions to real-world data in some of the problem sets. For instance, when we chose a function to approximate the light data from the EOAS building roof, or when we chose a function to approximate carbon dioxide increases in the atmosphere as measured by Charles Keeling. Well, in this case, I chose the function f of t equals 220 minus 15t minus 11.6 t squared plus 1.04 t squared plus 1.04 t cubed minus 0.02 t to the fourth plus 0.000168 t to the fifth. I also graphed it here for you so you can see how well it fits the data and also the places where it misses some of the wiggles in the data. Okay, now we've got this nice smooth function that we can use some of our mathematical tools to manipulate. Let's look at it for just a moment, because just looking at this graph tells us some interesting things about the pandemic. First, we can see that there are clearly two phases to the outbreak. We have the initial outbreak in Wuhan, China, which the Chinese government was eventually able to get under control through massive and mandatory quarantines, and a second and ongoing rise after the virus went global. We can also see that the rate of increase is not yet showing any signs of slowing down as the virus spreads around the world. We're currently seeing over 60,000 new positive tests every day. Another thing that we can do with this function is we can compute its definite integral to figure out how many new cases there were during any time span. For instance, If we compute the definite integral of f of t from t equals 0 to t equals 90, we're really computing how many cases there were from the beginning of the year until year day 90, which is the end of March. And that definite integral equates to the area under the curve. So in other words, the area that I've colored cyan in this graph. And if we compute this integral, we find that in the first 3 months of the year, there were 704,181 people diagnosed with COVID-19. Okay, that is computing the definite integral over the entire length of our graph. But we don't have to do that. We could ask the question, how many people tested positive for COVID-19 in the month of February from year day 31 to year day 60? In that case, we need to compute the definite integral of f of t dt from 31 to 60. Again, that's equal to the area colored in cyan in this graph. And if we compute that definite integral, we find that there were 76,895 people around the world who tested positive for COVID-19 in the month of February. We can also ask how many people tested positive during the first 2 weeks of March by computing the definite integral of f of t from t equals 60 to t equals 74. In that case, we find that 47,804 people tested positive in just that 2-week span. Of course, since we have this continuous function, we don't actually need to restrict ourselves to analyzing infection rates over monthly, weekly, or even daily periods. We could compute how many infections there were in only half a day. If we compute the definite integral of f of t dt from 89 to 89.5, we are asking how many positive tests there were between midnight and noon on the last day of March. This definite integral tells us that 36,476 people were infected in just half a day. That is almost as many as were infected in the first 2 weeks of the month combined, and shows you how rapidly this pandemic is progressing. From our standpoint, however, trying to understand integrals, one of the most important things to remember is that all of these definite integrals gave us numbers back as their results. Next, we'll move on to talking about the indefinite integral. An indefinite integral is the same thing as an antiderivative. It is a differentiable function, g of t, that has a derivative equal to another function, f of t. You can also think of it as being similar to the definite integral, but without upper and lower limits of integration. The most important 2 facts to understand about an indefinite integral is that if g of t equals the integral of f of t dt, then f of t equals the derivative of g of t. Note that there is also a constant in that equation for g of t. The constant is that little letter c that I colored in red. We'll come back to that constant in a moment. First, please note that indefinite integrals are always a function. This is very different from the definite integrals. The definite integrals typically give you a scalar value that is equal to the area under the curve. The indefinite integral, however, is a function. It's also really important to note that while the definite integral is defined analytically or geometrically, the indefinite integral is defined algebraically. Okay, let's get back to that little red constant for a moment. Please direct your attention to the figure on the top right. That's a really simple function. F of x equals x. So what is its antiderivative, g of x, going to be? Well, we know how to take the derivatives of polynomial functions, so we know that if we were to guess that 0.5x squared is the antiderivative of f of x, we could do a really quick check and see that the derivative of 0.5x squared is, in fact, 2 times 0.5 times x, which equals x. So 0.5x squared is an antiderivative of f of x. However, it is not the only antiderivative of f of x. Consider, for instance, if we tried g of x equals 0.5x squared plus 5. The derivative of 0.5x squared plus 5 is also x, because we know that the derivative of a constant is 0. The bottom graph shows 3 different possible antiderivatives. All of those functions have the exact same slope everywhere. They all have the exact same derivative. Thus, they are all antiderivatives of f of x. That is why the little plus c is there in red in the equation for g of t. When we take the derivative of g of t, that constant will just go away. It doesn't matter to the derivative. So we could have any possible constant in there, and it would still work as an antiderivative. Okay, now let's look at the indefinite integral with our COVID-19 infection data. The graph on top is again showing our function, f of t, that quantifies the number of new coronavirus cases per day. But this time, instead of just integrating it from one time point to some other time point, we're writing a function that equates to integrating from the beginning of the outbreak to some arbitrary time. So instead of just figuring out the area under the curve once, we actually need to figure out the area under the curve as we move along in time. That allows us to write a function, g of t, for the antiderivative. Remember that our function g of t is the integral of f of t dt, or in other words, the antiderivative of f of t. Of course, that also implies that the derivative of g of t must be equal to f of t. The derivative of the total number of cases with respect to time must be equal to the amount of cases per day, and the integral of the number of new cases per day should be equal to the total cases. Next, we need to figure out how to actually compute these indefinite integrals. Okay, the indefinite integral is the same thing as the antiderivative. So that means that if we have some function, which we will call f of x, and we want to find its indefinite integral or antiderivative, then what that means is we need to find some other function, g of x, such that the derivative of g of x is equal to f of x. Let's start off with something simple. We'll start off with the function f of x equals some constant a. The graph on top shows you this equation with a equals 6, so it's just saying that f of x equals 6. The bottom graph shows the integral if we integrate under the curve. Obviously, that's a straight line. This suggests that the indefinite integral of f of x is equal to a linear function. Specifically, it is equal to g of x equals 6x. For any constant a, we can write that the integral of the function f of x equals a will be equal to a times x plus some constant c. Let's check and make sure that actually works. Let's call our integral g of x and say that g of x equals ax plus c. Then let's take its derivative. The derivative of a times x is just equal to the slope, a, and the derivative of the constant c is of course 0. So that actually checks out. And we can see it in the graphs on the right. The top graph shows our integral function g of x equals 6x and shows its slope as you move along. The bottom graph shows the derivative, which is equal to the constant 6. So the derivative of the integral gets us back to our original function, f of x equals 6. All right, let's move on to something a little bit more complex. Let's talk about polynomials. The graph on the top shows the polynomial f of x equals 0.6x squared minus 2x. The bottom graph shows its integral, g of x equals 0.2x cubed minus x squared. As a reminder of what a polynomial function is, polynomials are functions that can be described as a constant a0 plus another constant a1 times x plus another constant a2 times x squared plus another constant a3 times x cubed and on up to an arbitrarily large exponent n that x is raised to. We refer to the polynomial as an nth degree polynomial if n is the largest exponent on the x. The derivative of an n degree polynomial is equal to a0 times x plus 1/2, the integral of an n degree polynomial is equal to a0 times x plus 1/2 a1 times x2 plus 1/3 a2 times x3 plus ... plus 1 over n plus 1 times a sub n times x to the n plus 1 plus a constant c. Note that in all of these, you replace the x to some constant with x to that constant plus 1, and you need to divide by the original exponent plus 1. Let's work through the derivative to see why this is true. All right, our antiderivative function is g of x equals a0 times x plus 1/2 times a1 times x squared plus 1/3 times a2 times x cubed plus ... plus 1 over n plus 1 times a sub n times x to the n plus 1 plus a constant c. All right, let's see why this works as the derivative. The derivative of a constant a0 times x is just that constant a0. Moving on to the next term in the equation, the derivative of x squared is 2x, so noting that the 2 in the exponent cancels out with the 1/2, the derivative of 1/2 a1 x squared is a1x. Continuing to the next term, the derivative of x cubed is 3x squared, so the 3 in the exponent is again going to cancel out the 1/3, and the derivative of 1/3 a2x cubed will equal a2x squared. Moving to the right, the derivative of x to the n plus 1 will be equal to n plus 1 times x to the n plus 1. So the n plus 1 in the exponent will cancel out with 1 over n plus 1. Therefore, the derivative of 1 over n plus 1 times a sub n x to the n plus 1 is equal to a sub n x to the n. And finally, we know that the derivative of the constant c is 0, so that just goes away. And we find that the derivative of dg dx is equal to our original function f of x. So this all works. But let me mention one other thing. This works even if those exponents are negative. For instance, the derivative of x to the negative 2 is negative 1 times x to the negative 1. However, there is one case for which it doesn't work. Think about x to the negative 1 for a moment. We know that x to the negative 1 is the same thing as 1 over x. But applying our function here, the integral of x to the negative 1 would be equal to 0 times x to the 0. But x to the 0 time is just a constant, and multiplying it by 0 gives us 0. That clearly can't work. There's actually something weird with the integral of x to the negative 1, or in other words, 1 over x. So let's talk about that next. The function f of x equals 1 over x starts off at infinity when x equals 0, but rapidly decreases after that as shown in the top right graph. It will always be positive, which means that its integral should always increase, but it will increase by less and less as we go along. And in fact, that less and less decrease over time is exactly equal to the rate of increase of the natural log function, or in other words, log base e. The integral of f of x is actually equal to the natural log of x. And you can see from those graphs on the right that that actually makes sense. But let's look at the derivative of the natural log of x to see if its derivative really does look like 1 over x. The top graph shows you the function natural log of x and the slope of its tangent line as you move along. You can see that the slope of the tangent line started off incredibly high, but got smaller and smaller as you went along. And you can see that is exactly what the function 1 over x does, because the function f of x equals 1 over x is the derivative of the function g of x equals the natural log of x. Okay, next let's discuss the integral of an exponential. Remember that e to the b times x is the function we use for exponential growth, where b is the specific growth rate of the population. We know that the derivative of e to the bx is equal to b times e to the bx. So it makes sense that the integral of e to the bx might be 1 over b times e to the bx. Let's check it. Let's take the derivative of g of x equals 1 over b times e to the bx plus c. The derivative of e to the bx will be equal to b times e to the bx. So that means that the b in the exponent will cancel out with the 1 over b. The derivative of 1 over b times e to the bx is thus equal to e to the bx. Again, the derivative of the constant is 0, so the derivative of g is in fact equal to our original function, f of x. Next, let's look at one of our trig functions. Let's look at the integral of f of x equals sine of x. You'll notice, if you're following along on the graphs on the right, that the integral definitely has to repeat with the same period as the original function. We know that the derivative of sine of x is cosine of x. We also know that the derivative of cosine of x is negative sine of x. So it makes sense that the derivative of sine of bx might be negative 1 over b times cosine of x plus some constant. Okay, let's check to make sure this works. We'll take the derivative of 1 over b times the cosine of bx plus c. Well, we'll note that the derivative of cosine of bx is equal to negative b times the sine of bx. So that means that the b inside the cosine will cancel out with the 1 over b outside the cosine. And so the derivative of 1 over b cosine bx will be equal to sine of bx. And as usual, the derivative of a constant is 0, so that goes away and our equation checks out. The integral of sine of x is negative 1 over b times the cosine of bx plus a constant. I'm not showing you here the integral of cosine of bx, but you should be able to figure that out for yourself. And in fact, I'm going to ask you to figure it out for yourself on the mini quiz. All right, Let's talk about a couple of rules that we can use for finding the antiderivatives of more complex functions. Let's remember that for derivatives, we have a nice rule for the derivative of sums. If f of x equals the sum of two other functions, g of x plus h of x, then the derivative of f of x is equal to the derivative of g of x plus the derivative of h of x. Okay, well, let's think about what the integral of f of x might be. Let's posit that the sum rule for integration might be the same as the sum rule for derivation. Let's posit that if f of x equals g of x plus h of x, then the integral of f of x dx equals the integral of g of x dx plus the integral of h of x dx. Next, let's check to see if this works. Well, this will work if the derivative of the integral of f of x is equal to f of x, or in other words, if it is equal to g of x plus h of x. So let's figure out what the derivative of the integral of f of x is. We will work on the right side of that equation. We know that since the derivative of an integral is the original function, then the derivative of the integral of g of x dx must be equal to g of x. Similarly, the derivative of the integral of h of x is equal to h of x. Now if we add those functions together, we find that the derivative of the right-hand side of the equation is g of x plus h of x. So that must be equal to the derivative of the left-hand side of the equation. So we know that the derivative of the integral of f of x dx equals g of x plus h of x. So that actually checks out. Okay, that integral rule works. We also had a rule for taking the derivative when we multiply by a constant. If f of x equals a constant times g of x, then the derivative of f of x equals a constant times the derivative of g of x. Let's see if a similar rule will work for integration. We will posit that if f of x equals a times g of x, then the integral of f of x dx equals a times the integral of g of x. Now let's check it. Well, working on the right-hand side of the equation again, we know from our rule for the derivative of multiplying a constant that the derivative of a times the integral of g of x dx must be equal to a times the derivative of the integral of g of x dx. Of course, the derivative of the integral of g of x dx is simply equal to g of x, so this term becomes a times g of x. And that checks out. So we have these two new equations that allow us to compute the integral of a complex function that is either the sum of two other functions or is equal to a function multiplied by a constant. However, if you'll remember before, we had a lot more rules for derivatives, including the multiplication rule, the quotient rule, and the chain rule. Unfortunately, those simple rules for derivatives won't work for integrals, but we'll get back to that in our next toolbox. All right, we've talked about definite integrals and indefinite integrals. Definite integrals calculate the sum of the area under the curve between two limits, which is equivalent to summing the function over infinitesimally small intervals. Definite integrals typically return a scalar value for you. On the other hand, we have indefinite integrals. Indefinite integrals are equal to the antiderivative and hence give back a function when you compute them. Next, we need to talk about how indefinite integrals relate to definite integrals. If g of x equals the indefinite integral of f of x dx, then the definite integral of g of x from x equals a to x equals b is equal to g of b minus g of a. This is a really important concept and is actually one of the core concepts of integral calculus. So let's take a moment to go through it slowly and see why it works. We're going to go about as simple as we can, and we're just going to make f of x equal to a constant value. We'll say that f of x equals 2. Then let's ask the question, what is the definite integral of f of x dx from x equals 1 to x equals 5? Well, we know that the antiderivative of a constant is simply equal to that constant times x. So we can write that the indefinite integral of f of x, which we'll call g of x, is equal to 2x plus c. Remember, c is just any constant. We can pick any constant c, and this equation will still work as the antiderivative. So let's just pick one. Let's pick 3. So g of x equals 2x plus 3. Now we know that we can compute the definite integral of f of x from x equals 1 to 5 as g of 5 minus g of 1. And we can figure that out pretty easily. We know that g of 5 is 2 times 5 minus 3, which equals 13, and g of 1 equals 5, so g of 5 minus g of 1 equals 8. Now let's look at a graph to convince ourselves that this really is correct. The graph shows f of x in the blue line, and the red box shows the limits that we are integrating over with our definite integral. So that means the definite integral has to be equal to the area of that red box. That red box has a height of 2 and a width of 5 minus 1 equals 4. So what's the area of a rectangle of height 2 and width 4? That area is equal to 8, so that all checks out. Now let's work on a problem that is a bit more important. Let's pull up the equation that we wrote at the beginning of the lecture to estimate the number of new coronavirus cases each day. F of t equals 220 minus 15t minus 11.6 t squared plus 1.04 t cubed minus 0.02 t to the fourth plus 0.000168 t to the fifth. This equation estimates the number of people diagnosed worldwide with the coronavirus each day as a function of time, t, where time is the number of days that have passed since the beginning of the year. Here's a graph of the function that actually goes out a little further into the future. Note that year day 100 is April 9th, and I'm recording this on March 29th, so this is now a prediction 11 days into the future. Alright, next let's use the tools that we've learned to compute the integral of f of t, which will allow us to estimate the total number of people that have gotten the coronavirus. The antiderivative of f of t is equal to 220t minus 7.5 t squared minus 3.9 t cubed plus 0.26 t to the fourth minus 0.04 t to the fifth plus 0.000028 t to the sixth. Let me go through this real quick to make sure everyone knows where this equation is coming from. The integral of 220 is 220t. The integral of 15t is 15 times 1/2 t squared. The integral of 11.6 t squared is 11.6 times 1/3 t cubed. The integral of 1.04 t to the fourth, 1.04 t cubed is 1.04 times 1/4 t to the fourth. The integral of 0.02 t to the fourth is 0.02 times 1/5 t to the fifth. The integral of 0.000168 t to the fifth is 0.00168 times 1/6 t to the sixth. Okay, so that's the integral of our function, and it should tell us how many people have been infected. Let's see what it looks like. All right, the graph on the top is our number of coronaviruses per day, and as we're going along in time, we're integrating the area under the curve to get our integral, our definite integral, which I've graphed on the bottom there. You can see that it stays essentially flat until around year day 40, when in February we started to see an increase in the number of cases in Wuhan, China. The integral then levels off a bit before starting to rise again steeply in March as the coronavirus spread around the world. Now, remembering what we learned about how our antiderivative relates to the definite integral, let's figure out how many people have tested positive with the coronavirus. Okay, the total number of cases from January 1st to April 9th should be equal to the definite integral of f of t dt from year day 0 to year day 100, which is equal to g of 100 minus g of 0, which equals 2,029,400. So by April 9th, we should expect over 2 million total positive tests worldwide. All right, let's try another one. If we want to compute how many positive tests there have been so far, and by so far I mean until I'm recording this on March 29th, we can compute the definite integral of f of t dt from 0 to 89, which is equal to g of 89 minus g of 0, and equal to 626,730. Let's try one more. Let's try to figure out how many new positive tests there will be in the week from March 29th to April 5th. For that, we'll compute the integral from x equals 89 to 96 of f of t dt, which equals g of 96 minus g of 89, which equals 722,920. So that suggests that there will be more infections in the coming week than there have been throughout the entire year so far. That's a sobering thought, and the reason that epidemiologists are so worried about COVID-19. All right, with that less than cheerful thought, we're going to wrap up this toolbox. Please make sure to take the mini quiz on Canvas.